Good afternoon. Nice to meet you, everyone. My name is Nadia. I'm an application engineer at MathWorks. I am based in our Glasgow office, which is in Scotland, quite far up north. So it's quite cold today now. We really have kind of winter. I hope it's warmer where you are. And I'm going to give you an overview of the kind of modeling, simulation, and testing capabilities for wireless communication systems with MATLAB. So there's a lot to cover, but I will try to really just give you an idea of how everything would work together. And I'm happy to take any questions at the end. We'll dip a little bit into cellular standards, but also satellite communications, a little bit on hardware, but I won't go too much into detail, but you can ask a question, I can try and answer. Yeah, it's quite a broad, quite a number of broad topics I'm going to cover on the waveform generation side for different wireless standards. Then how we put all these together with a channel model, you end up with the end-to-end link level simulation. Then we're going to change topic a little bit to satellite, and that's quite relevant because it links with the sort of 6G exploration coverage analysis, which is one of the drivers is non-terrestrial networks. I've had a lot of interest in that this year. And we're going to also look into a little bit beyond just physical layer into above to MAC layer for network level simulations as well and what capabilities exist there. Let's get started. This is a kind of graphic that just demonstrates where at MathWorks we are investing our time and effort in the wireless space. So we try to cover from algorithm to production. So that would be cellular standards. You can see there's quite a lot of products there related to different wireless standards, including some add-ons which are just free to download when you have the base toolbox, like for example, 6G Exploration Library. On the right-hand side, when we think about a wireless system, it is not just digital side, right? The baseband. There's also the antenna, RF, all this stuff starts to play into the system and have impact. We can start to build system level models from the digital and the RF together. We can also model and solve our antennas or import from third-party antenna solving tools and build up a much bigger picture of how our system looks like, a behavioral model. Lastly, when we're happy with our algorithm and we've analyzed any impact of, for example, RF or power amplifying nonlinearity into our waveforms, we might be ready to start prototyping it and deploying it. So for that, there exists ability to auto-generate code, whether it's HDL code or embedded C, C++, and additional IP blocks that can just be used off the shelf, for example, forward error correction and so on. In addition to that, there is infrastructure to control test and measurement equipment when we set up the test bed in the lab, so we can test as we go and then get through to production. So we're going to really just scratch the surface. There's so much more depth we can go into, but this just to give you an idea. Oh, of course, now the latest hot topic, is artificial intelligence, right? So it is not coming from like MathWorks deciding that artificial intelligence is something people need to look at. It's actually being driven by the industry itself, who are asking us about AI, including 3GPP, the standardization body, who have working groups looking at AI for the air interface. All of these wireless kind of capabilities that we have are kind of working in an ecosystem with the AI tools that we have, which I have not even listed them here, but deep learning, machine learning, and so on. And we're working on many examples to demonstrate how these work together. AI isn't part of my topics, but I can take questions on that as well. What are the typical challenges when we're talking about wireless communications? In many cases, we have to abide by a standard set by IEEE or 3GPP. So we have to read and understand what the standard tool says, and we have to come up with some ways to implement that. So that's a really thankless task. It's a many pages, a lot of reading and understanding, and very likely to make mistakes. When we do that, then we have to develop an actual algorithm. We have to choose a language, to write this in, we have to write the code and we have to confirm that it does somehow fit the standard. To confirm that it fits the standard, we have to test and validate that. Maybe we test and validate with third-party tools, maybe with a gold reference, maybe with some other mechanism. So that takes a really long time, and one of the largest amounts of time is really on the testing and validation to make sure we are standard compliant. Of course, the purpose here is that we have already done the work for you, whether that's for 5G or LTE or WLAN or any of the SATCOM standards. We already have provided these implementations, so you can actually focus on what matters. You can focus on where you put your IP, your own custom part. You can focus on the system outside of the standard if you don't care about the standard. You can focus perhaps on the RF front end or the specific components you need to purchase, and then not on, for example, the specific standard. So the various wireless standards toolboxes, and I'll jump in and out of the different ones, they have a number of applications and use cases. You'll see it kind of repeated across all the standards toolboxes. They allow you to generate a standard compliant waveform, which is very important when you need to, for example, test equipment or compare perhaps against another implementation. You have the full range of available parameters according to the standard. In addition to that, when there's implementation of the channel model and an example receiver, or you perhaps make your own receiver, that's your kind of IP, you can now make an end-to-end simulation and test things like throughput, block error rate, etc., packet error rates, and so on. So you can validate the impact of various modulation coding schemes, various channel conditions, and so on. So you can test the robustness of your algorithm. On the test and measurement side of things, you can investigate things like EVM and adjacent channel leakage ratio, which are very important when it comes to standard to conformance testing for either base station or UE, which depends on which test you want to make, and whether you will be complying with spectrum restrictions you have imposed on you to not leak into adjacent bands. It becomes really important when you're changing, for example, RF components and they have an impact on your waveform. There's examples to show you how to do that. Lastly, there are some examples that demonstrate signal detection from live signals. So you can record a signal from the air using a software-defined radio or test and measurement equipment. If it has an antenna, you can record that and you can bring that into MATLAB and do some blind packet detection for WLAN or something like MIB and SIB1 recovery for 5G. I already mentioned that there is support for hardware and radio connectivity, so you can use that to set up a test bed and drive that directly from MATLAB. And you can also use software-defined radio, which then you can start to play some of your algorithm on the fabric, on the FPGA, on the software, on the system on chip that lives on the FPGA. So you'll see this sort of theme repeated for any of the standards toolboxes. Okay, if we jump into the first one, generating standard compliant signals, it is very straightforward to start generating any waveforms that are standard compliant. You can start off with what's called the Wireless Waveform Generator app. It's a great starting point for all of our customers, really, because you don't have to write all of the code. You can just use the drop downs and they tell you which parameters you can use. So if I just switch to MATLAB, maybe first I'll show you how to navigate to these things. Let me know if it's maybe too small. Hopefully it's big enough, the text. But if you are looking at the documentation page for any specific products, you will see that they are roughly divided by like the categories I spoke about. Waveform generation, this is downlink, uplink, signal reception end-to-end, system level, this is what I'll talk about later, network level, and test and measurement. So you can kind of navigate and find that it's very similar for 5G toolbox or LTE toolbox. You see very much a similar structure here on the waveform generation side, downlink and uplink, signal reception, end-to-end test and measurement. So that's where you can start finding various examples or capabilities. So on the 5G toolbox side, let's go back here. If you look at the various examples, you can get started straight away with waveform generation. So the way you get started with that is under the apps tab. There's many different apps that appear depending on your license profile, but what you're looking for is the wireless waveform generator app, which I've already opened in advance. So it looks like this. And depending on your licenses, you will see which waveforms you can generate here. So I've got everything installed. So I know I can generate 5G, LTE, WLAN, Bluetooth, and satellite, and even radar, and even custom sort of non-standard specific, like some OFDM waveform. So if I just go into something like for the 5G, these, if you're unfamiliar, these FRCs are called fixed reference channels. They're used specifically for testing. They have a restricted parameter set because it can become very overwhelming very quickly. There's lots of parameters, but you can see here that I can choose either for FR1 band or FR2 band, which opens different parameters for me. I can choose the modulation coding scheme, the subcarrier spacing, the bandwidth of the signal, whether it's TDD or FDD. And I can very quickly get a visual understanding of the frequency on the y-axis and the time in slots on the x-axis like this. In addition, I can choose to apply filtering myself if I wish, or any oversampling that may be required if you're testing, for example, some RF components and you need to capture the out-of-band components. Having the waveform oversampled is a, for example, a requirement there. In addition to this, you can already apply some impairments you may want. So this is like perfect clean waveform. Then we can choose to apply some impairments, AWGN or a phase offset with some degrees. So we can add that in if we choose. Once we're happy, we can hit generate. And we will see, so because this is a TDD waveform, the spectrum doesn't look that good. But if I just have one that is fully allocated, we can see our spectrum. We can see some measurement like CCDF. We can also look in the time domain or a spectrogram. And then we can look at the channel view, which becomes really helpful, especially if we start to look into mixed numerology type of waveforms for 5G, for example. So this is like restricted set. This is where we can get started with. But what we can do is we can basically translate this now into the full parameter set. So we can start with something simple, then open up all the rest of the parameters. So this will copy this restricted set into the full configuration, and you'll see we'll get way more options there that we can change for the different channels in the 5G waveform. So the complexity is really imposed on us by the 3GPP spec. There's a lot of complexity there, and it's not the easiest thing to handle. You need to understand what you're doing, but we try to make it easier for you to get started. So you can see now I can actually choose a different subcarrier. I can do like a mixed numerology sort of thing. This is probably not gonna. If you make a mistake, for example, if I look at the channel view now, I've got two carriers. If I make a mistake here, I think it will say, nope, you have to define it like this. You cannot define how you want because of this bandwidth you have and so on. So it will tell you where you've gone wrong to try to fix it. So this is my first bandwidth part, second bandwidth part doesn't have anything there. And there's all the additional signals open up to me to modify as I want. The user data, the control, channel state information, and so on. So it really does the complexity, the 3GPP is being kind of captured there. So once I'm happy with my waveform, I can do a few things. I can export to the workspace, call it, I don't know, my 5G wave. And I can also export to a file directly, save it, or I can export to MATLAB script. So let's take a look. I already exported it to the workspace. So let's have a look what it is. My 5G wave. You see we have my waveform, time domain, and I also have metadata. What is it? .config. Then I can see what the actual configuration of everything is. Save one, let's look at waveform. Okay, my full configuration is here. So if I export it then as MATLAB script, I get all the underlying MATLAB code. And you can see it's a lot of code, which is why we have tried to make it easier in an application. And then at the end, once we have our configuration, we're just calling one function, which is NR waveform generator. We get our waveform, and then we add any impairments are added on later. So this is exact same thing as this. And what happens is if you need to create maybe test Monte Carlo, you can just for loop, put this in a function, put a for loop, I don't know, 10 different options. But what you can do is you can then change your, for example, your channel bandwidth can be 60 or whatever is your I of something. You can just loop around these things, generate them very quickly that way.